So yeah, the recording for some reason was not starting, so it started now. Okay, so as I said, we'll be switching back and forth between matrices and linear transformations, right? I mean, representing matrices induced by linear transformations, right? I mean, some of you have been wondering what the heck is a linear transformation. We'll talk about that. But one of the foundational things about linear algebra, or the reason why linear algebra has become so popular, particularly in the last 50 years, with the emergence of computing, is because the complex geometry from lower dimensions to higher dimensions can now be represented in a very elegant and eloquent manner by using linear algebra. Okay, so you no longer have to face the trouble of not being able to visualize stuff in the higher dimensions, because you have an appropriate representation of quantifying that. Okay, so let me go back to the PowerPoint presentation. And also, what I wanted to tell you is that, I mean, we did finish at the rotation matrix, and then I think some of you have made an interesting observation about the eigenvalues of the rotation matrix, right? Hold that thought for some time, because we are not going to get straight away to the eigenvalues of the rotation matrix. Before that, we need to talk about what an eigenvalue are, what eigenvectors are, right? Okay, these are stuff that we have talked about in the previous lectures. Okay, so I'll just jump straight onto these geometric operations. Before that, let me remind you that we have a superficial idea about what a vector space is, what a span of a vector space is, what is a basis, what is linear independence, what is linear transformation, right? What happens when you impose a linear transformation from one vector space to another vector space, right? What is a dimension of a vector space? How do you compute dimension of a vector space, right? Okay, how can we use linear transformations to represent certain geometric operations, right? Okay, all right, and these are some of the things. And then we have also talked about an application of a linear algebra, which is principal component analysis. I'm going to come back to some of the results of that we have actually used to compute the principal components, right? I mean, and those couple of results that we just talked about, and we just have seen empirically from the correlation matrix, where that if you have a real symmetric matrix, then the corresponding eigenvalues are real and distinct, right? And the corresponding eigenvectors are orthogonal to each other, right? Okay, and therefore those corresponding eigenvectors are also linearly independent. Okay, all right. So these are just a refresher of what we have done the other day. Okay, so you can use linear transformations to represent any one of these, right? Okay, and this is what scaling means. Okay, a visual representation. It could either be a dilation or a contraction. This could be a rotation, right? Okay. This is just a 2D translation, which is nothing but a shift operator, right? So you start from the origin, you go to one place in the two-dimensional position coordinates, and from that place you go to another place. The question that you should ask is that where you stop, that final place, right, which also has generated a vector, that final coordinate, can it be represented using the initial coordinates, which is the origin? Turns out, yes. If you exactly know the amount of the shift, you can. Okay, how do you achieve that? You achieve that by using a matrix, which means a matrix of the corresponding linear transformation plus some scalar addition, which is represented using a column vector. Okay, all right. So now, I mean, I would still be, talking a little about matrices, right? Because, I mean, you are familiar with the matrix structure. You know what an identity matrix is, right? And you know what an if I have a matrix, what do you mean by the inverse of a matrix, right? I mean, I think in school and first year of college, the way you have understood inverses is that if I give you a matrix, right, you compute the determinant of the matrix. And if you see that the determinant of the matrix is non-zero, then you say that the matrix has an inverse. Okay, nothing wrong in that. The only problem is the determinant approach is not encouraged for a bunch of reasons. Okay. All right, now since we have been talking about linear transformations, so let me go back to the whiteboard. Okay. So let me just say these once again. Matrices and their properties are equivalently represented by the inducing linear. Okay, so what does this mean? What it means is the following, that if I have a matrix, okay, if I have a matrix, so in this case, I mean, what you have seen in the slide is that for a matrix A, sorry, is this the right place? Yeah. So for a matrix A, in order to have an inverse, it must satisfy this property, right? Not only that, it has to satisfy both of this, okay, which means the matrix itself or the corresponding linear transformation should have a left inverse as well as a right inverse. And since your approach of figuring out whether the matrix has an inverse or not solely dependent on determinants, you also know that unless a matrix is a square matrix, you cannot compute the determinant of that, right? Okay, so the same thing applies as far as linear transformations are concerned. Okay, so if we define a linear transformation over here, right? If we define a linear transformation from one vector space to another vector space, and both of the, since I am using the same vector spaces, needless to say that the dimension of the vector space where your linear transformation resides, and then by virtue of this linear transformation, you are actually creating a beautiful image onto the image space, which is also the vector space. Since I am representing both of these spaces by the same notation V, I imply that the dimension of these two vector spaces are the same. And therefore, by virtue of inducing the linear transformation, I am actually creating a square matrix. Okay, all right. And in fact, what I should do is that I should call this the matrix A induced by the linear transformation. Okay, all right. Now, you also know that an identity matrix is nothing but you have the element 1 along the principal diagonal of that matrix, and everything else is 0. The same applies to an identity linear transformation. So whichever terminology you are familiar with earlier, right? I mean, we're going to replace those terminologies by the equivalent terminologies in linear transformation. Okay, all right. So an identity matrix will be replaced by an identity linear transformation. All right. So what this means is, let me just erase this now, or rather not. I mean, I don't really need to erase this. So what I should do is, it's an equivalent statement that we need to cook up, which is T inverse T equal to T inverse, and that must also be equal to the identity matrix. Okay, all right. Now, what exactly is a linear transformation? As I told you in the other class, right? I mean, you would be better off if you think of linear transformations as just functions. It's a very special kind of a function. Now, functions can be anything. It can be a nonlinear function, right? There are exponential functions, logarithmic functions, linear functions, transcendental functions, different types of functions, right? Now, a linear transformation is a very special type of a function, okay, which satisfies a couple of properties, okay, all right? And these properties are the following. I'll just write it down in the following fashion. In fact, this is the property of the additivity, right? And this is the property which we call as the scalar multiplication. Okay. Now, the x and y are elements which are drawn from your vector space V. Okay. And alpha is just a scalar. So while x and y are column vectors, alpha is just a scalar or a number. Now, the question is this. I mean, it's an interesting question, right? And you should be able to answer that. Where does this definition of linear transformation come from? I mean, I know many of you are familiar with this, structure of a linear transformation. You know that linear transformations are defined this way. But my question is, where does this weird, structure or definition of a linear transformation come from? The answer is actually intuitive. I'll give you 1 minute, maybe 90 seconds to think about it and answer the question in the chat box. So just follow the two properties, okay? T of x plus y, which means you have a transformation or an operator, just an operator. It could be any operator. You have an operator which is applied to a sum of two column vectors. And what you get on the right hand side is that the same operator applied to those individual column vectors, and you take the sum of that. And both of these are same. Now, a careful introspection and inspection, I mean, if I take my function as t of, for example, if I take my function as, if I just write my function as t of, x square, will the first property satisfy? What do you think? No, right? No. Why not? Because the function that I defined, I mean, to begin with, or constructed to begin with, is a nonlinear function. Okay? All right. However, let's go back to what we have been discussing. So let's forget that for a moment, right? I mean, let's forget that for a moment, right? And let's focus on this. So why does this particular structure of linear transformation is appealing? And why we should be working with this particular structure of a linear transformation? Anyone? That is all right. Oh, that's fine. All this is fine. I mean, don't tell me the obvious thing. Okay. There is a reason why I wrote a matrix structure, and just below the matrix structure, I wrote the structure of a linear transformation. And you'd do well to remember that whenever I talk about a matrix, I mean that a matrix is induced by that corresponding linear transformation. Yes, Maitrish, very good, excellent, right? See, look, I mean, if you look carefully, the first property, doesn't this property fit exactly when you have matrices? Also look at the second property. Doesn't this second property fit the matrices as well, right? You have a matrix, you have elements in a matrix, and what you do is you do an element wise, you multiply each element, right? I mean, each element by a scalar, and then what happens? You can just pull the scalar out, correct? Okay, so therefore, both of these properties perfectly fit a matrix, okay? Because what happens is a matrix, let me, probably, I think I'll write it here, okay? A matrix is nothing but a linear operator, okay? All right, okay? So these two properties satisfy for any matrix. Okay, all right. And so that's the reason the linear transformations are defined in such a way that you can actually directly map a matrix corresponding to a linear transformation. Is this clear? Right? I mean, this definition did not come from moon, right? I mean, it just, the linear transformation is defined specifically so that it suits the purpose of constructing matrices. Okay, so with this in mind, so I hope you guys are taking notes, because this screens I cannot be saved. Okay, the software that I don't, but I can't save this, so I'll have to erase this now. Okay, all right. So therefore, I mean, what we are going to do is that just go quickly to the slide, right, and look at one of the properties of inverses of matrices. Okay, all right, and see whether these properties of matrices are true or not. Okay, there is one other thing, right? I mean, as I said, your idea of inverse of a matrix, or corresponding the inverse of a linear transformation, solely depended on the fact that if you are able to take the determinant of the matrix and show that the determinant is non-zero, right? It's a computationally expensive procedure. But I also said that a matrix, a linear transformation, is nothing but a function. Okay, which means that you would do well to remember from your first calculus course. I don't know whether it's high school or first year in college, but your first calculus course, when do you say that an inverse of a function exists? When do you guarantee that the inverse of a function exists? What is the necessary and sufficient condition for the inverse of a function exists? Because linear transformation is also a function. The same condition will apply to linear transformations as well. Recall that a function, in order for a function to have an inverse, it needs to be 1 to 1 and 1. Okay, all right. So therefore, it's a bijective mapping. There has to be a function, has to be a bijective map as well. The same applies to linear transformations. In order that a linear transformation and the corresponding matrix possessing an inverse is solely dependent on the fact that the linear transformation is a bijective mapping. Now, what do you mean by a bijective mapping? Is basically what you have is that you have two elements here, two elements which are different from each other. You map them onto this image space, which is another vector space of same dimensions, right? And then when you map them, it's basically the image of those elements, right? So if you have x and y two elements here, t of x, which are different from each other, then their corresponding mappings should also be different from each other. Okay, and for every element here, you will have the corresponding image map. Okay, all right. So now let's just see this in the light of. So what I intend to tell you is that, let's say you have a vector space here, which is V. You have another vector space, which is also V. Okay, let me call this W, okay, for now. And what I'm saying is dimension of V is equal to dimension of W. Okay, all right. Now, what I am doing is that by virtue of a linear transformation, which is T, okay, I am just building an image set of the elements in V and pasting it here. Now, this dimension of the image space may or may not be equal to the dimension of this entire vector space W, but that is okay. That is once again the exactly what you have studied about range, right? Okay. So now, are you able to define another linear transformation, P inverse, which goes from W to V in such a way that when you have a composition of those two transformations, which is what? What is composition? The composition is nothing but T inverse as well as T inverse T. The composition could be in any direction, okay? All right? Both of these should be equal to each other and should be equal to. Then only you say that the inverse exists. So you are no longer dependent upon what is the exact structure or dimension of your matrix? Can you compute the determinant or not? Okay, this is the reason I love this approach of linear transformations. Okay, instead of going through the Hoffman-Coons or Gilbert-Strang way of computing large determinants and blah blah blah. Okay, all right. So now, if you recall, I have, if you go back to the PowerPoint slide, I have a property. There they use 3 matrices. Let me just use 2 matrices. Okay, all right. So what basically this particular slide has is the following, that they're claiming that AB inverse is nothing but, sorry, let me write it here, is nothing but B inverse A inverse. Okay, all right. Now what I would want to do is to write, as I said, I am going to do everything in terms of linear transformations, right? So let's say the matrix A is induced by the linear transformation T, and matrix S, B is induced by the linear transformation S, then this guy, TS inverse, is nothing but S inverse T inverse. I'm sorry, did I mess it up? I think I did. Okay, let me write it again. So TS inverse is S inverse T inverse. Okay, do you believe this? Well, I would like to, but I mean, what is the deal? I mean, how are we going to sort of see that this is indeed the case? So let's try this, right? Now, since you know that if you take the composition of 2 linear transformations, what do you expect? You will actually generate another linear transformation, right? Because if you have one function f, another function g, you take the composition of those 2 functions, f compose g, you actually produce another function. So the same principle works here, correct? Okay, so what I mean is, so let's say I have TS from the left, TS inverse, and you know that this has to be the identity transformation, right? Right? TS inverse has to be the identity transformation. Okay, all right. And then let's look at the other guy. What is the other guy? The other guy is S inverse T inverse. Now, if this is the inverse of TS, then this must also satisfy this relation. Wouldn't you agree? Right? This has to satisfy, right? I mean, how does it satisfy this relation? It's very simple, right? I mean, you know that matrix multiplication is not commutative, but it is associative, right? You know that, right? Okay. So if I come back here, so I can just club these 2 guys together. So this becomes T inverse T. Now, what is T inverse T? T inverse T is nothing but I. Now, what we have now is S inverse with an identity matrix with S. Now, S inverse with an identity matrix will give you S inverse, and then S inverse with an S will give you an I. So what do you see? You see that you have 2 equations. TS times TS inverse is equal to I, and S inverse T inverse times TS is also equal to I. Actually, what I should have done is I made a mistake. I'm really, really sorry. I should have done it the other way around, right? I mean, how do I? Okay. 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 Okay, so I'll just have to redo this, I guess. Okay, so since I was doing operations from the left, TS times TS inverse is this, then TS times, let's look at TS times S inverse T inverse. This would also be equal to I, right? Okay. All right. Now, so we have TS times TS inverse equal to I, and TS times S inverse T inverse is also equal to I. Now that means what? These two guys are equal to each other. And then you have these are actually vector spaces, are actually subspaces of a field. Are you familiar with the properties of groups, rings, and fields? No, I mean in discrete mathematical structures. That would be strange. I mean, okay. All right. So are you familiar with left cancellation properties and right cancellation properties? So what I imply is that, you know, if 5 of x equal to 5 of y, then 5 is cancelled from the left side and you get x is equal to y. As simple as that, right? Now, when you have numbers, I mean, anyway, the order of the multiplication doesn't matter. But when you are dealing with matrices, the order of the multiplication matters, right? So you either have to cancel from the left or you have to cancel from the right. Okay, all right, not a big deal. So in this case, what you are doing is you're actually canceling from the left because you have the same term TS on both equations. So you can cancel from the left. And if you cancel from the left, what are you going to get? You are going to get this, right? Aren't you? You are going to get this. TS inverse is equal to S inverse T inverse. This is an important property of inverses of matrices. Okay, clear? Okay, so this is actually our first proof in the class. We haven't proved anything before. Okay, so the first proof is simple proof, but I mean, there are certain things that you need to keep in mind. I mean, you cannot cancel arbitrarily. You are no longer dealing with numbers. Okay, so when you are canceling, you have to cancel from the left or you have to cancel from the right. Okay, now if you revert the order of operation, okay, you are going to get the same thing. Okay, all right. So whenever we talk about existence of an inverse of a linear transformation, we mean the left inverse as well as the right inverse. Both have to exist. And needless to say that the transformation has to be defined from a vector space to another vector space with identical dimensions, so that you actually end up getting a square transformation. Okay, all right. Okay. So, and then transpose. This transpose is like, I mean, you have an Excel sheet, right? I mean, you cut one column and paste it as a row, or cut one row and paste the elements in a column, right? And that is exactly what a transpose is. So once again, transpose of a matrix is equivalent to transpose of a linear transformation. And if you take the transpose of a transpose, you get back the original matrix. Okay. If you have two matrices or two linear transformations and you take the transpose, it follows the same rule in terms of order as the inverses. Because in inverses, what we have seen is that AB inverse is B inverse A inverse. That same thing applies to transposes as well. That AB transpose is B transpose A transpose. Okay, and then there is another algebraic property that is nice about transposes, and this does not apply to inverses, unfortunately, that A plus B transpose is A transpose plus B transpose. You cannot say the same thing about inverses. Okay, all right. Now, one question is, I don't know whether you are familiar with this, and some of you might be familiar. Why do we care about transposes? Have you seen an application of a transpose in a practical machine learning problem that you have solved? I know most of you have done a lot of machine learning projects, right? Any idea, guys? Any of you, have you seen an application? That's not an application. Vectorization. Don't throw keywords at me. Dual. No. Don't, I mean, all right. To find the weighted sum in machine learning problems. What does that mean? How many of you have solved regression problems? Or how many of you have worked on a regression problem in your mini project or internship? A lot of you, right? A lot of you, right? So typically what happens when you solve a regression problem? Let's say we're trying to solve an image processing problem. And you want to express the images and the pixels in terms of systems of equations. You can do that, right? So your rows basically are just the images and columns are the pixel values, correct? Just imagine. And typically what do you expect? In a very large database, I mean very dense images, the number of pixels, if you do a 1024 by 1024, how many pixels are we looking at, right? So typically the number of columns are more than the number of rows. It could happen, right? Right? So even any other application, right? You're solving a system of equation. Haven't you come across a situation where your number of rows or number of equations are actually smaller than the number of variables? Or the other way around, right? Yes. So what do you do in such cases? You are not able to solve such systems? Is that what you are telling me? Or are you able to solve such systems? So I'm not hearing anything from you. Are you able to solve such systems? Yes or no? You don't know. I mean, if you have worked with regression problems, you should know this, right? That situation is very, very common, right? So such matrices are irregular matrices. Because their number of rows and number of columns are not equal, right? What do you do in such a case? Let's say, we have transformation which is non-square. Okay, all right, which is non-square, which means the corresponding matrix is also a non-square matrix. And we are actually dealing with a situation of you have a system of equations. We still need to find the solutions. We can't say we can't find the solution. We still need to find the solution, right? So which means, in order to, that if you have a system, let's say y equal to tx plus b, right? Y equal to tx plus b, where t is a transformation which induces the matrices, right? Your y's are known, your b's are known, and you just need to figure out the inverse of the matrix T, right? You still need to compute the matrix T. So the thing is that T is non-square. This T guy is non-square. And I still need to deal with it. So what do I do? I don't know where is your mind today. I'm sorry to say. Maybe it's too late in the day, and I'm sorry for that. But we have a non-square matrix, and we somehow still need to figure out the inverse. Then what do we do? If we can't figure out the inverse of a non-square matrix or a non-square linear transformation, what choices do we have? Okay, let me ask you a question. Are you familiar with pseudo inverses? Guys, are you familiar with pseudo inverses? No. Okay. All right. Okay, if you have a non-square matrix, okay, all right. If you have a non-square matrix, can you not multiply that non-square matrix with its transpose? Yes or no? Forget the identity. You cannot directly compute the identity of a non-square matrix. But let you tell me this. T is a non-square matrix, okay? All right. And T is a non-square matrix. And I have T multiplied with T to the T. Okay. All right. Then what happens to this matrix? And let's call this T star. So what happens to P star? Yes, it becomes a square matrix, right? Okay, now, I mean, I cannot compute the inverse of the original T, but can I compute the inverse of T star? So I can compute the inverse of T star. Okay, all right. And this is known as pseudo inverse, which is used left and right in multiple linear regression problems, not simple linear regression problems, but multiple linear regression problems. Okay, used heavily in multiple linear regression problems. Okay, all right. Now, what you typically do is that you have this guy, right? Y is equal to tx plus b. So what you do is you multiply both sides of this equation by a T transpose. Okay, so that, and then you compute the inverse. Okay, all right. And then that is known as the pseudo inverse. And using the pseudo inverse, you should still be able to find out this x, because that is what you need to know. You don't know these x's, you need to find out this x's. So that is where the usefulness of a transpose comes in. Otherwise, why the hell would I take the transpose of a matrix? Right? Usually, if I am given a square matrix, okay, so that's one thing of a transpose, right? One utility of transpose. What is the second utility of a transpose? A transpose shall tell you if a transformation is symmetric or not, right? Okay, all right. And what happens if a transformation is symmetric? If a transformation is symmetric, the corresponding eigenvalues are, I mean, the real symmetric transformation, the corresponding eigenvalues are real and distinct, right? Then you have a bunch of very nice results which you use directly in PCA. Okay, so a very simple operation, very simple algebraic operations have actually very useful significance. Okay, all right. So this is not pure abstract stuff. Okay, all right. So let's go back to the slide. So you have a transpose. Now there is another useful property of a transpose is that there are very special types of transformations which are known as orthogonal transformations. And this has a direct connotation in many machine learning applications. And if a transformation on a matrix has to be orthogonal, then this property has to be satisfied, which is the transpose of the transformation and the inverse of the transformation are exactly the same. Okay, all right. And A nice example is a diagonal matrix, because a diagonal matrix, if you take the inverse of it or if you take the transpose of it, both times you'll actually end up having the same result. Okay, all right. Okay, okay, good. So now what we wanted to, so let me go back to the whiteboard. Okay, and let's erase this. All right. Okay, so now, so we talked about transposes, we talked about inverses of transformations, and we need to know what sort of results, what kind of things that we are able to do. And before I talk about these kind of projections and stuff, as I promised, let's go back to the first lecture where we claimed certain things, right? We claimed that, I mean, if I have a real symmetric matrix or a real symmetric transformation, linear transformation, if the eigenvalues are real and distinct, then the corresponding eigenvectors are orthogonal to each other. Okay, so let us recall what an eigenvalue eigenvector equation is. Okay, so we all know that it is Tx equal to lambda x. Okay, this is important, and as we keep talking about the geometric interpretation of this particular equation, I mean, I think probably in college, whatever matrix algebra you are exposed to, you are familiar with setting this up, solving the characteristic equation, finding out the different values of lambda, and then plug it in, finding out the values of different x's, and that's it, right? If I ask you a question, what does this equation imply geometrically? Can you tell me? One thing is this, that I have a column vector, okay? I have a column vector, and what I'm doing is I'm multiplying that column vector by some scalar, okay? Some arbitrary scalar. I'm also multiplying that column vector by a corresponding linear transformation or a matrix. So the left-hand side is a matrix vector product. So when you multiply a matrix with a vector, what do you expect to get? What do you expect to get? You expect to get another column vector, or in the language of linear transformation, it will be an image in the image space, right? Okay. Now, what you see on the right-hand side is that image is exactly equal to the original vector multiplied by some random positive number. Isn't that weird? Okay. Isn't that weird? What do you think? Well, what does it really mean? It means this. Let's say I have this. So here is my transformation applied on the vector, and here is lambda x could be here, it could be even here, here, or anywhere, right? But it is always on this line segment. There is no reflection, there is no rotation. You get that? Okay. Now, what is this Tx? I mean, basically this Tx is a line segment. Would you also agree this Tx is nothing but the span of that vector x? So you are actually doing as I said, I mean, if you go back to a linear transformation thingy, right? I mean, a linear transformation can do a lot of things for you. It can do a scaling, it can do a rotation, it can do an identity, reflection, shifting, everything, right? Okay. However, in this particular case, what you are doing is, I mean, it is not doing reflection, rotation, or any of that stuff. It is keeping the output exactly in the span of the original vector. So this eigenvalue eigenvector dynamics is something that will never let the input vector fall off the span of it. So what I mean is that I cannot really sort of imagine something like this. Okay, I mean, it's nothing like this will not going to happen, this will not going to happen, this is not going to happen, this is not going to happen. Okay, so it will always stay in its span. Okay, so that's the geometry of it. All right. Okay, so now let's come back to the original question that we should answer. Is that what I know is this, that t of x equal to lambda x, and this t is symmetric. Okay, what I mean by that is that this t is nothing but t transpose. Okay, all right. We also know that the lambdas are real and distinct from each other. So let's say I have two lambdas, lambda 1 and lambda 2. Okay, so if you have two lambdas, you should actually have two representations of eigenvalue, eigenvector. So tx1 equal to lambda 1 x1 and tx2 equal to lambda 2 x2. Oops, so damn this. I'm going to clear this off. Okay. So let's write here. So tx1 is lambda 1 x1 and tx2 is lambda 2 x2. Okay. All right. Now let's do a little trick. Okay. Let's take the transpose on both sides. I can do that, right? And just now you have seen the property of a transpose, right? What happens when you take the transpose of two things? I mean, the order will change. So therefore, by following that approach, you will have x2 transpose t transpose. That is the left hand side. What do you have in the right hand side? On the right hand side, lambda is a scalar, right? Lambda is a scalar. So when you take that, and so the only vector that you are dealing with is x2. So, and if you take the transpose of a scalar, it remains the same because it's just a number. So don't worry about lambda. So lambda 2 will remain lambda 2, and this will be x2 transpose. Okay. All right. Now, what I can do is, we also know that we have another interesting property here that we should leverage. Your T is a symmetric transformation, right? Which means what? Your T transpose has to be T itself. So therefore, in the next line, what I can write is the following, that x2 transpose T, because I can just replace the T transpose with T, is lambda 2 x2. Okay, so far so good. Now what I will do is, I will multiply on the right by the other vector x1. So what I will do is, I will have an x1 here and I will have an x1 here. Okay. Why I did that will be clear in a minute. Let's look at this in the next line. So we have x2 transpose, and this, what is this tx1, guys? You see it right here, right? This tx1 is nothing but lambda 1 x1, right? On the right hand side, you have lambda 2 x2 transpose x. Okay, so far so good. Now look, there is a lambda hovering on the left-hand side in between, but lambda is a scalar, right? So I can pull that lambda. I can write lambda in any order when we are multiplying stuff, and it doesn't matter. You cannot do the same thing for vectors, but when you have scalar, you can do that. So what I can do is I can get rid of this lambda 1 here, and I can just bring this lambda 1 over here. And therefore, in the next line, what I can do is I have lambda 1 minus lambda 2 x1 transpose x2 equal to 0. Would you agree with this? One minute. This will be. This is from. Actually, I should have erased this. This is lambda 1. Okay, would you agree? Now, what did we say? We said that this lambda 1, lambda 2, there are two, these two are different from each other. So that means your lambda 1 minus lambda 2 cannot be equal to 0, right? Because lambda 1 and lambda 2 are two real distinct eigenvalues. So what does that imply? What does this imply? This implies that the only possibility is that x1 transpose x2 equal to 0. What do we know about this? We also know this x1 transpose is nothing but the inner product of x1 and x2. Okay, are you getting these, guys? So if I have a symmetric transformation, symmetric linear transformation with eigenvalues real and distinct from each other, then what do I say about the corresponding eigenvectors? That you have to tell me this. What do I say about these corresponding eigenvectors? The corresponding eigenvectors are? No, orthogonal, just orthogonal. We don't know whether they are linearly dependent or not. Excellent. Okay, so this is, do you remember, we used this result in PCA. We looked at that correlation matrix, and that correlation matrix, if you recall, the elements of that correlation matrix were 1, 0.916, 0.916, and 1. And when we found out the eigenvalues came out to be 0.916 and 0.0084, if I recall correctly. So these are real eigenvalues distinct from each other. And then we claimed that if these are real eigenvalues and distinct from each other, and this correlation matrix also by visual inspection turned out to be symmetric, then the corresponding eigenvectors would be orthogonal to each other. If you recall, the values of those corresponding eigenvectors in the PCA problem is that one eigenvector was 1 over square root of 2, 1 over square root of 2. The other eigenvector was 1 over square root of 2 and negative 1 over square root of 2. You take the dot product or inner product of it, your end result would be 0. Okay? All right. Fantastic. Okay. So are you getting this? Okay. All right. So we are just defining things. We are talking about things which are in and around the concepts of linear transformation. No. You see, if the eigenvalues are distinct, so you have a real and symmetric linear transformation, and if the eigenvalues are distinct, then the corresponding eigenvectors are orthogonal to each other. Okay, I did not say that the real and distinct eigenvalues follow from that. Okay, all right. There is a proof, and we will get to that. I mean, but I really don't want to do a lot of proofs now. I mean, I'll just do things slowly. Okay, but this proposition is based on the fact that I have a real and symmetric linear transformation, and I know that the eigenvalues are real and distinct. That is why I said, look, go back and look at the PCA example, right? And then you make a claim that the corresponding eigenvectors are orthogonal to each other, and which we exactly did, empirically as well as theoretically. Okay, so remind me that in the next class when we begin, our first thing that we should do is that if a set of eigenvectors, or if a set of vectors are orthogonal to each other, then the corresponding, those vectors are linearly independent. No, yes, you are right. You are right. I mean, that's why I said the assumption is if the transformation is symmetric and the eigenvalues are real and distinct, okay? Because the eigenvalues could be real and similar to each other also. Okay, all right. Then this relation will not hold, which is why the theorem says this: a linear transformation is real and distinct. The eigenvalues are, sorry, a linear transformation is real and symmetric. The eigenvalues are real and distinct, and then the corresponding eigenvectors are orthogonal to each other. Okay, all right. So this forms the basis of our next lecture, which will be on Friday. We are not having a class on Wednesday. We'll have it on Friday. Okay, guys, that's it. Thank you.